Hello. So we learned in the previous video, what is the R-square. R-square captures the strength of the linear relationship or the how good your regression model can explain. Uh, However, so like back to our example of returns to education. Now the R-square is only zero point 0.1. It explains only 10% of the data of the dependent variable. That means, so in here, we would like to predict the hourly salary, hourly wage using education, but only 10% of hourly wage is explained. Then can you say the model is bad? Actually not. So earlier in our earlier example, that was made up numbers. So I could explain 93%, but in practice, 90% is too good to be true in most cases. Think about this now. Think about this. How many factors determine your hourly wage? There are numerous factors, but we only use one of them, education. So education by itself explains 10%. So in that sense, if you think that way, 10% is huge. One variable can explain 10% of your wage determination, then that's really important factor in your wage, right? So in that sense, it's not that surprising and your model is not that bad. 10% explaining 10% of wage is pretty a good job. Of course, if you include more information, more variables, you could do better. That's what we are going to do. So the next step, if you are not satisfied with 10%, so it's reasonable, 10% is reasonable, but you could do better if you use more x. So for example, as an example, I'm going to extend your equation to include another variable, right? So earlier there was only beta 0 and beta 1, but now I add beta 2. And because so it's not a big problem. Interpretation is not a big problem. So earlier, so we interpreted beta 1 as the marginal cost or the effect of x on y. But when you have another variable, you have to be a little more careful when you interpret beta 1. So it should be interpreted this way. Beta 1 is the effect of x1 on y. That's no difference. That's exactly how we interpret it. But you have to add this condition. When x2 is fixed. So it's the ceteris paribus assumption common in economics. So when x2 is given, fixed, x2 does not change, beta 1 captures how much y changes when x increases by 1 unit. That's how you interpret the coefficient when you have more than one variable. Everything else is the same. So beta 1, the OLS estimators will be unbiased. They will be most efficient. And you can calculate the confidence interval in the same way. And everything else is the same. Statistical significance calculated in a similar way. Prediction can be done in a similar way. Residual can be done in a similar way. So pretty much the same. If you understand how you did them, the same intuition, same structure holds in multiple regression. We call this multiple regression because there are multiple variables. Fitted value is calculated this way. So you estimate beta 0, beta 1, beta 2. Excel will do that for you. So you can predict y fitted value is given by using those estimates. And then plug in the point where you would like to predict. The residual can be calculated as the difference between y and y hat. So it must be simple. So what I'm going to show you now is, now I collected another variable, age. So let me just call this salary. So we would like to predict salary using education and age. So as you get older, your salary will increase as you age. So age may be relevant in your salary determination. So let's try this again. Data analysis and regression. And here, input y range, y, the dependent variable is wage, and x range is these two variables. You have to include column A and column B both in x. Okay, then now I'm not going to show you the line. I will show you this. Okay, try this. So then the problem here is the scatter plot is not easy to make because there are three variables. You cannot make three-dimensional plot. Your plot is only two-dimensional. So you have to make separate scatter plot for education and salary and age and salary. So again, the idea is the problem is now it is not a line because as I said, it's originally you have to consider three-dimensional space. So you are just summarizing, like compressing that to two-dimensional. So the predicted value is not exactly one line because in three-dimensional there are different straight lines at different cross-section. So it looks like this. So now scatter plot is not that helpful. Just you need more techniques to make a better looking, better scatter plot. But this table is pretty much the same. There is no difference in the structure of this table, right? So the only difference we have is an additional line, additional row. So because we had additionally have age variable, so this part is a new one. So that's how I take it. So now then we have point estimators for the intercept beta 0, beta 1, beta 2, and their standard errors and confidence intervals, t-stat, p-value. I will ask you this question. Suppose that there is a person whose age is 30 years old, and he or she finished 16 years in school, like finished college. What is the predicted wage, predicted salary, according to your regression? Simple algebra. Okay, you can use those numbers. So intercept is minus 0.075, and the coefficient of age is minus 0.048, and coefficient of education is 0.741. So plug in those numbers, estimate, and then I have fixed the age to 30, education to 16. So plug that in. Simple calculation, simple algebra will give you 10.341. So prediction is no difference. Pretty much standard, right? Now, then how about statistical significance? So we have t-stat and p-values from you read the table and see what are the statistically significant variables among these. So I will consider only education and age, exclude intercept, and among those, between those two variables, which are statistically significant at 5%. So you just need to look at the p-value. Remember, for the variable to be statistically significant, you should reject the null hypothesis. So p-value should be smaller than 5% here, but age has a p-value of 20%. Education still has 0%. So education is rejected. Education's p-value is smaller than 5%, but age is not. Age's p-value is greater. So you can reject education only. So education is the only statistically significant variable among those two, right? So the answer is education. Age is not statistically significant. Back to I deleted the plot. So if you had the scatter plot, so this is scatter plot with respect to age. So as you can see in the scatter plot, it looks like it's flat. If you make a trend line, it looks like flat. That means flat means the slope is 0. The direction of the relationship is 0. So statistically insignificant. Statistically, the slope looks like 0. So the minus sign here, if you look back at the results, the coefficient of age is negative, which is very counterintuitive. But you can think it as a random error. Estimation error happened, so like it could take a negative value. Otherwise, it would be 0 or slightly positive. Anyhow, statistically, you cannot exactly estimate what it is. But also another thing you can find here is R square is still around 10%. So including age did not help much in terms of the R square. So still so without age, we could explain 10%, around 10%, but including the age, still it's 10%. So addition of another variable did not help that much. So that's reflected in the statistical significance. That's because age is not statistically significant. So it does not help explaining the salary. So that's why R square did not increase much. However, what's annoying here is including age affects all the other coefficients. So education coefficient is actually different. Earlier, the coefficient of education was 0.743, but now it's 0.741. Slight change, but still it's a difference. So including another variable not only changes the coefficient itself, but other variables' coefficients are also affected. That's the thing. So when you include more variables, you have to recalculate everything. Of course, Excel will do it, so it's not a big problem. Okay? So I briefly showed you how to extend a model to multiple variables. So that's pretty much it for the main theory for regression models. Now, I will spend a few more minutes as a caution when you use the regression model in practice. First, I'll show you an example. This ice cream and intelligence, interesting variables. So the Economist, the prestigious magazine, economics magazine, reported that ice cream consumption induces anti-brain freeze. So if you consume more ice cream, your brain will work better. So it's evidenced by a strong relationship between ice cream and PISA. It's a standardized test ranking across countries. So it uses nonlinear regression, but basic idea is the same. And R square is 49%. 49% of test score is explained by ice cream consumption. Surprising. So the higher reading score is associated with larger ice cream consumption. So you can find it real column about this research result from the Economist webpage. Isn't it surprising? Would you consume more ice cream? Why then? Why schools do not give you ice cream, or why don't you have an ice cream before the exam? Because it's absurd. So it looks like the data is not wrong. Data is true. Regression method is true. There is no problem in the graph. But the problem is in the interpretation. What it tells you is that there is a strong linear relationship, but it does not say ice cream causes your intelligence. Ice cream induces anti-brain freeze. There is no causality. Causality is not a direct implication of this statistical result. So look at this. So it was published in 2016 April. Actually, it was published on the April Fool's Day. So it was just it's to fool you. You are fooled. So then put it this way. Then how can we interpret this? Of course, ice cream consumption has nothing to do with your test score. That's obvious, but right, common sense. Then why do we have this strong relationship? Because ice cream consumption is associated with the economic growth, development. Like like affluent countries will consume more ice cream, and affluent countries will spend more money on education, and they are concerned more about education, reading scores, right? Developing countries cannot consume ice cream and cannot spend money on reading, like of young kids. So that's the relationship. That's why they are strongly correlated. Okay? So what you have to learn from here is the regression results only imply statistical association. But from here, if you want to say causality, cause and effect relationship, you need economic theory or other theory. Like, so when I say education increases salary, that's not because of the statistical result, but because your economic theory, intuitively, higher education induces better salary. So that's not statistics, right? On top of that, we use statistical method to quantify the exact amount of that causality, right? And there are more examples about this. Like, for example, what's interesting, another common and famous interesting example is the number of pirates and global warming. According to the data, if you have more pirates in the Caribbean, then the global warming could be prevented. Of course not, but like as an example of malpractice of regression analysis, the pirate and global warming is considered. So number of pirates have been decreasing over time, but global warming has been increasing over time. So it looks like they have strong negative relationship. Okay. Now, another thing you have to worry about is possible nonlinear relationship. So when the linearity fails, the results is meaningless because we have assumed linear relationship, but the practice is the really could be nonlinear. So one example is pollution and GDP. So usually it is okay. Usually it's acceptable to say that GDP, economic growth, causes pollution. That's okay. But the problem here is they are not linear. Like first, when developing countries develop, they cannot take care of the pollution. They cannot take care of the environment. So when an economy grows, pollution grows together. But at a certain point, they start to take care of the environment. So then since then, the pollution goes down as the economy grows even further, right? So they have like hump-shaped, inverse U-shaped relationship, which is called Kuznets curve. But so the pollution goes up and then goes down. This kind of nonlinear relationship cannot be handled by the linear regression model. So I have an Excel, but I'm not going to show you that here. It's pretty obvious method. And so as a last word, it was a brief introduction to linear regression model. And if you want to study more, I strongly recommend you to take economics 420. So this course is 320, and 420 is the next step for data analysis in economics. So in that course, it's a fully semester of regression model. Variations of regression models will be studied all semester. So that will be more useful in actual data analysis. So in this course, I spend more time on introductory theories and more simple algebra because that's what introduction has to do. But if you want more applied flavor, I strongly recommend you to take 420. I'm not teaching that course, so you can take it from another professor. And I'm teaching another data analysis course for undergrads. That's 480 statistical causal inference. I will teach how to make causality, how to estimate causality from data. So I will teach that in spring. So if you're interested, I strongly recommend you. I would love to have you in that course. So please uh, register, or you can ask me if you are good uh, for that course or if you're interested. Okay. Thank you for the nice semester. Like I understand it must be very boring and could be difficult throughout the semester, but you did a great job up to here. Okay, then have a nice winter and have a nice rest of your life. See you later. Bye.